Hello, my name is Hongyang Sun. I'm from Vanderbilt University. In this video, I'm going to present our paper, Resilient Scheduling of Moldable Jobs on Failure-Prone Platforms. On large-scale, high-performance computing platforms, being able to efficiently schedule parallel applications is extremely important in terms of improving the application performance, as well as the system utilization. Further, as the size of the systems becomes ever larger, the error rates will also increase dramatically. Thus, being able to handle job failures will be critical for the resilience and reliability of future scientific computing. This paper combines these two important research directions, namely job scheduling and failure handling, for multiple parallel jobs subject to failures. So what is a moldable job? In the scheduling literature, parallel jobs are typically classified into three categories. Rigid jobs are jobs where the processor allocations are fixed by the user and cannot be changed by the system. Hence, these jobs have fixed and static allocation. For multiple jobs, the processor allocations can be decided by the system, but once the job has started, they cannot be changed. Hence, these jobs have fixed but dynamic allocation. Lastly, a job is a malleable job if the processor allocation can be dynamically changed by the system during runtime, thus having variable and dynamic allocation. In this paper, we consider moldable jobs because they can easily adapt to the amount of available resources while being easy to design and implement. In fact, many computational kernels in scientific libraries are provided as moldable jobs that can be deployed on a wide range of processors. In this paper, we study a scheduling model in which unmoldable jobs are to be scheduled on p-identical processors. The execution time of each job is a function of the processor allocation, and the area of the job is defined as the product of the processor allocation and the execution time. Jobs are subject to arbitrary failure scenarios, which are unknown ahead of time, so the problem can be considered as semi-online. I will discuss more about failure scenarios in the next slide. The objective is to minimize the makespan, or the successful maximum completion time of all the jobs. In particular, we consider several common speedup models. In the roofline model, a job has perfectly linear speedup up to a maximum degree of parallelism. In the communication model, a job has a communication overhead when using more than one processor. A job under the Amdahl model has a perfectly parallel fraction and an inherently sequential fraction. The monotonic model is a general model, requiring the execution time of the job to be a non-increasing function and the area of the job to be a non-decreasing function of the processor allocation. And finally, in the arbitrary model, the execution time of the job can be any arbitrary function. We consider silent errors or silent data corruptions in a failure model. Specifically, jobs can be hit by a silent error during runtime, leading to the wrong computation result. A lightweight silent error detector is assumed to be available to detect such errors at the end of each job's execution. If the error is detected, the jobs must be re-executed, possibly many times, until it successfully completes without error. Formally, a failure scenario is defined as a vector specifying the number of failures each job experiences during a particular run. In the example shown in this figure with a total of 5 jobs, you can see that job 1 has 2 failures, job 2 has 1 failure, and all the other jobs have no failure. Notice that here a failed job must be re-executed following a failed run. Our main contribution of the paper is the following. We propose 2 resilient scheduling algorithms. One is list-based, called LPA-LIST, and the other one is batch-based, called batch-LIST. We analyze their theoretical performance in terms of the approximation ratio under several speedup models. And recall that a scheduling algorithm is a C approximation if its makespan is at most C times that of uh, an optimal scheduler for any job set under any failure scenario. We also conduct extensive simulations to evaluate and compare their average and worst case performance against some baseline heuristics. Let me now introduce our first algorithm, LPA-LIST, which employs a two-phase approach to schedule the jobs. In the first phase, a local processor allocation strategy is used to minimize a local ratio individually for each job. This will be guided by a property of list scheduling, which I'm going to talk about in the next slide. Once the allocation has been made, and they will remain unchanged throughout the different execution attempts of the job. Therefore, in the second phase, the allocations of the jobs are fixed, and the list scheduling algorithm is used to schedule all the jobs. In particular, the jobs are first arranged in a list in any order, and then scheduled one by one at the earliest possible time, with backfitting included whenever possible. If a job fails after an execution, it will be reinserted back into the queue and rescheduled later until success. One important property of the list scheduling algorithm is that if the total area of all jobs under a processor allocation can be bounded in terms of the optimal total area, or a lower bound, say by a factor of alpha, and if the maximum execution time of any job can be bounded against a lower bound, say by a factor of beta, then a list schedule is guaranteed to have an approximation ratio R, where R is a function of alpha and beta as given in the equation 1 here. This equation can then be used to guide the processor allocation policy made by the LPA algorithm, in the sense that it can simply minimize this ratio for each individual job separately. And then, because of the property of the maximum and the summation function, the same bound will be applied to the whole job set. We are able to show that the LPA-LIST algorithm achieves a constant approximation for three common speedup models, namely a 2 approximation for the roofline model, a 3 approximation for the communication model, and a 4 approximation for the Amdahl's model. In particular, the result for the communication model improves upon the best result known so far obtained by Harwell and Mao without any resilience considerations. The algorithm, however, has a relatively high approximation for the general monotonic model in the order of root p, and this is due to its simple but uncoordinated processor allocation strategy, which we'll improve upon in the second algorithm. Our second algorithm is a batch-based algorithm. It's called batch list. It organizes the different execution attempts of the jobs in batches that execute one after another. In each batch K, the pending jobs are only allowed to execute a maximum of 2 to the power of K minus 1 times. If a job is still uncompleted after that, it will be handled by the next batch. The figure here depicts how the batch list algorithm schedules the execution of 5 jobs in 4 batches under a particular failure scenario. Well, that was the general idea of the batch list algorithm. So what happens within each batch? Well, within each batch, the processor allocation for the limited number of execution attempts of all the pending jobs are decided collectively using an algorithm proposed by Lapère, Tristram, and Wegener. The algorithm guarantees a near optimum processor allocation while working for SPDAGs or trees, of which a set of independent linear chains induced by job failures is a special case. Once the processor allocations have been decided, these jobs are again scheduled by the least scheduling algorithm. Overall, the batch least algorithm achieves constant approximation within each batch and produces at most log Fmax batches, where Fmax here is the maximum number of failures of any job in a failure scenario. So therefore, the algorithm gives an overall order of log Fmax approximation for the problem. We then evaluated the performance of our algorithms using simulations based on synthetic jobs that follow different speedup models and parameter settings. Failures are generated following exponential distribution with an error rate lambda. Two baseline algorithms are used for performance comparison, and they are mean time and mean area, which allocate processors to minimize the execution time and the area of each job respectively, and then use least scheduling to schedule the jobs. We also experimented with 3 priority rules that have been shown to give good performance when scheduling parallel jobs. And they are longest processing time, highest processor allocation, and largest area. The first set of simulation results, by fixing the number of processors to be 7,500, the number of jobs to be 500, and the error rate to be 10 to the minus 7, shows that our algorithm performed better than the baselines. In particular, the mean time algorithm performs well for the roofline model, but performs badly for the communication and Amdahl's model, while the mean area algorithm performs the worst for all models. In terms of the 3 priorities, we can see that longest processing time and largest area have similar performance, which is better than the performance of highest processor allocation. We then studied the impact of different parameters. By varying the number of processors, we observed that our first algorithm, LPA-LIST, has better performance for the roofline model, thanks to its simple and effective local processor allocation strategy. Our second algorithm, batch list, then catches up in the communication model, and it has the best performance in the Amdahl's model. And this is due to the increasing inefficiency in these 3 models in terms of parallelizing a job, as well as batch list algorithms coordinated processor allocation. The same observation can also be made when varying the number of jobs, as shown in this slide, as well as when varying the error rate, as shown in this slide. In particular, as the error rate increases, we can see that the performance of the batch list algorithm, our second algorithm, starts degrading. And this is consistent with our theoretical analysis that the approximation ratio increases logarithmically with the maximum number of failures of all the jobs. Now, to summarize the simulation results, both of our proposed algorithms perform significantly better than the 2 baseline algorithms. Overall, our best algorithm is within a factor of 1.47 of the optimal on average, and within a factor of 1.8 in the worst case. Throughout the whole set of simulations we have conducted. The table here shows the average and worst case ratios of the 2 algorithms with the mean time algorithm for 3 speedup models. Note here that the mean area algorithm is not included because it has very bad performance for all the speedup models. To conclude the paper, future shared clusters will demand simultaneous resource scheduling and resilience considerations for parallel applications. To embrace this need, we proposed two resilient scheduling algorithms for multiple parallel jobs with performance guarantees. Extensive simulation results demonstrate the good performance of our algorithms under several common speedup models. For future work, we plan to analyze the average case performance of the algorithms. For instance, when certain failure scenarios occur with higher probability than the others. One could also consider alternative failure models, such as fail stop errors, instead of silent errors, as well as the use of checkpointing to avoid restarting a job from scratch whenever there's a failure, therefore improving the overall scheduling efficiency. And finally, we would like to validate the performance of our algorithms by using more realistic speedups from actual applications and practical failure traces. I hope you find our work interesting, and thanks for watching.